What is this structure called? What is this structure called, this thing that we're solving? Okay, each one of these is a ratio. So together, what is it called?
Ratio pair.
Yeah, the whole thing, I don't know how to show that. Anyway, the whole thing is a proportion. So two ratios set equal, that's a proportion. So what's it called? Yes, a ratio pair. All right, so we're going to take our cross products and use parentheses. Okay, and then distribute. Remember, you'll get a middle term when you do that if you're doing it correctly. So m squared, of course, and then we'll get negative 4m plus 3m. So that's negative m, and then minus 12. How do we solve this kind? How do we solve this kind? Yes, but what first? Yeah, we need to get it equal to 0. And that's because it has the bx term. What is the bx term in this? Negative m, yep, negative 1m. All right, anyway, now we can do star, and there is no GCF. Hopefully you checked. What is a times c? Negative 56. Negative 1 for m, and then a is 1. Are there factors of negative 56 that add up to negative 1? Negative 8 and 7. Good. So we'll do x plus 7 times x minus 8 equals 0, and then we solve those two factors. Are you guys getting where you can do it without having to set up the equation like I just wrote? Like solve the factors? Good. All right, negative 7 and positive 8. How'd that go? Raise up how many you got. There were 2 answers, so raise up how many you got. She's trying to flip me off right there. Did you do it? How many did you get? 2, good. Okay. All right, well, that was solving a proportion. They don't really get much worse than that, just so you know. If you can work through a quadratic proportion for this course, you're fine. We will have some next course, meaning in Algebra 2, that are a fair bit uglier than this, but it's as long as you're good at factoring, they will probably go just fine as well.
I like these ones better. Like I like the quadratics more than the non-quadratic.
Oh, good. That's cool. All right, yesterday we talked about kind of a lot of stuff. So I'll put it up here. You can look in your notes too. Are you going to do that the whole time? It's okay. Proportions and proportional is kind of what this unit is about, except for we extend that concept into similarity. Mathematical similarity involves shape as well as proportion. We did talk about the word, the phrase or the concept scale factor, which is the thing that you multiply by. So it's not, we're never going to say divide, but it's what we multiply by to get a image length from pre-image length, or what we called the new length from the original. And so you just divide to get it, like new divided by original. That gives you the actual scale factor. And we did our solving proportions based on your feedback. That looks like it went pretty well today. We'll check the homework, but we're still kind of just reviewing this idea. Actually, let's do the homework check right now. Well, actually, I want to talk about this. There's something for everybody here. You've all probably at least seen one or both of these things. Do you agree that they are generally made to look like the real thing, right? Now, not Barbie, but maybe her house, right? Do you guys know Barbie is like all out of proportion? Did you know that? Anybody play with those kind of dolls? Yeah. I mean, they're kind of humanoid looking, but their proportions are weird. So, but the cars are designed to be a model of the real thing, and so we would expect all the proportions to be roughly the same. In other words, like, I don't know how far I can zoom in, but like if we took the door, it's kind of shaped like that, we would expect it to be a scale model of the real door. So maybe 1/50th the scale or something. I'm not super familiar with that. Does anybody know if it says the scale on the package? Does anybody know that? Doesn't say it there. Anyway, an Acura NSX is a real car, but it might say the scale factor. Okay. But if they designed it in a way that it wasn't realistic looking, it wouldn't be as cool. Unless it's meant to look like that. So these things that we're talking about in math class are actually being applied out there. If it says just going with what I said, if it says 1 to 50, that means it's a 50th the scale, which means the lengths are 50th the size, etc. Okay? Now that one's probably a little bit smaller than that. Okay, again, here's another application of this. So why might it be important to have scale drawings and models when it comes to design and building? So thinking of blueprints, architectural plans, those kind of things. Maybe it's even just a design on your own paper at home to make something. Why is that important? Think about it for a second.
Because you can't draw the actual size of a house. You can't make a house size drawing. So you have to scale it down to where it's still accurate, but you could draw it on the
Okay.
paper.
Still accurate. That's important, right? The relationships between the components need to be accurate, even though, like he said, we want it on a different size paper. Architectural plans are about half the size of this table up here. So if I drew a line this way through the table, a set of, each page in a set of blueprints, as we call them, they're about that big, maybe just a little bit bigger. They're pretty big. And if you have a big job, you have a roll of these. Usually you roll them up. That's maybe this big around and probably weighs 10 or 15 pounds. You're packing these things around. It's kind of crazy. But every page of that gives you some kind of information about the accurate relationships between pieces. All right, quick review before we go check homework. So you can either write this down or just look at it and think, but go ahead and find both scale factors. Is that you playing music or something? Raise your hand when you have both so I know when to move on. Okay, so A to B, what's the scale factor? Okay, 1/2. In fact, let's just write out how we get that. Remember, it's new over original. Because of the direction that it specified, the new length is 3 and the original length was 6, which we can reduce to 1/2. Okay, going the other way, what's the scale factor? So let's do the other side. So 4, the new side is 4, the original was 2, and so that's 2. What do you notice about those two? Yeah, what's that called in math? Yep. Okay, so depending on the direction, your scale factor is just the reciprocal. But do note also, there's no division, right? We're multiplying by 1/2, we're multiplying by 2. Also, it's a lot different, so make sure you get the direction correct. All right. Scale factor. One more time, we can find the length of CD, but I just want to talk scale factor. What's the scale factor? What, you should ask me a question right after I say that. So what's the scale factor? Say it. Okay, so she's asking which direction. Since we just did this problem where it specified a direction, this one doesn't obviously specify a direction. But if you read closely, which direction are we actually looking?
CD.
Yeah, we're going small to big, right? Because we want to know CD, so we must be asking for the scale factor from small to big. So it won't always tell you which direction, but you can kind of infer that from what's being asked. Now, you can take time to find the scale factor as 5 and then multiply 16 by 5. Does everybody see where I got that? But you can also just set up a proportion, which is what we will do, and that's what you were practicing on your homework. And I only gave you those few problems so you could get your feet wet with it. So remember the solving part is easy. It's the setup that's critical. So we need to be careful and set these up accurately. So I put the 30 in there. What else do we need to fill in? We need to set up an accurate proportion. Let's see how you picked up on this from yesterday. I need 3 other numbers for the total of 4 in our proportion.
The original value of 16 below 30, and then you need, can you just call it X, if you don't know it?
Sure, we can call it X.
So
I'll put an X right here.
So it'd be 30 over 16, and then,
30 over 6.
oh yeah, 30 over 6, and then X over 16.
Okay, so why did we have to edit when we were heading off into the 30 over 16? Why was that wrong? Yeah, we got to make sure to match corresponding parts, right? Now, is this the only one that we can write? The only correct proportion? So give me some more. There's actually 4 different versions that are accurate and okay to solve. What's another one? Good. So that's kind of 2 versions of that same setup. And then let's switch the setup now. What's another method?
X over 16 equals 30 over 6.
Oh, well, let's call that the same, since it's just the reflexive property of equality. Okay, I want you to look this way. Aren't those ratios also set, meaning they have to be the same? Right? So what kind of proportion could we write going that direction instead? Okay, I'll start you off. 30 over x equals what? 6 to 16. Okay, and then of course we can flip that over. Okay, and notice any of these four, diagonal multiplication multiplies the 16 and the 30. So it's doing the same thing, but it's thinking about it completely different. And here's what I mean. If we label what we're doing, and we always need to be consistent, I want you to label the 30, and I would say big and right. Do you see how it's the big figure right side? Okay. And then this is small right. And then over here, what would you call X? I would say big base, maybe. It's the big figure, the base. And then 16 is small base. So here's the consistency that I want you to note. We went big to small, big to small. So that's consistent. We went right side to right side, base to base. That's consistent. And you can always double check that you've set it up correctly by comparing your description. Okay, let's do, this is going to look a little differently. A little different. That's big right, the 30, and the X is big base. The 6 is small right, and then 16 is small base. So what's the consistency in that one?
Big, big, small, small.
Yeah, big to big, small to small. So that's consistent. And then right to base, right to base. And if you flip it, like if we happen to over on this side, sorry, that was good timing. If we happen to flip this one and do small to small, but we did base to right, then that wouldn't match right to base. So always go back, just if you're ever concerned, and make sure that you're matching the correct description. Because if you don't, it's going to be the wrong proportion. And you have that flexibility. In fact, there's a lot of times when going this direction, what I call in one figure, is easier, like going here to here. This case, it's not, but sometimes it is. So, I mean, in this case, it doesn't totally matter either. So with that said, let's go look at that homework. Yesterday, we set up the two proportions for X and Y in number 16. And for X, you guys said X to 2 and 18 to 6. So if we describe those, I would say X is short and 2 is short. So that's short to short, and then 18 and 6 are both the long sides. So it's short to short, long to long. Okay? Short, short, long, long. And we don't always necessarily know which one is short and long if we don't have numbers given. Okay, so the proportion is there. I'm not going to go down and write it below. So this becomes 6x equals 36 and x equals 6. Okay, what was the proportion for y? What was the proportion for y? Y to 5 equals 18 to 6. Now, usually I tell students to start with a known one, like 18 over 6, just because you want that. You won't be able to solve if you don't have it. Okay, so we get 6y and then 90, I think. 5 times 18, yeah. So y is 15. Okay. How would you describe that ratio, just kind of keeping that concept? Y and 5, what would you describe those? Because we already have long to long on the right side. What's y and 5? Yeah, medium to medium. All right. Again, we're not worried about specifically doing little to big, because sometimes you don't see it that way. And honestly, I don't care which way you do it, as long as it's accurate. Okay, what's our proportion for x this time? I'm going to start you off with that. What do you have to fill in to match? Good. 15 to 45. Okay, if we were going to describe this, maybe we would say like short to long in one figure now instead of across figures. Okay, if you went 3 to 15, that's short to short. I'm doing short to long. Does it matter? No? Okay, so this is 135 divided by 15, which is what? Did anybody do that?
9.
What is it?
9.
9, thanks. Okay, 18. By the way, why are all these angle notations in here, do you think? Yeah, it helps you to know which one corresponds. That's what we're doing right now. Also, we're going to see how you prove that two triangles are similar, and angles are part of that. So that's another reason. We just haven't gotten there yet. All right, set up the proportion. Braden, how about you? Will you set up this one? Yeah, do you feel ready to do that?
Maybe. I don't know if this will be right, but I did 3 over x minus 4
All right, I'll start writing 3 over x minus 4.
equals 5 over x.
What do you guys think? Does that look good? Okay, so we get 3x equals 5x minus 20. And 2x equals 20, so x equals 10. And then ED, we just go back and plug it in, so ED is 6. All right, so these kind, number 19, here's my advice on these. This is the first one we've seen that's kind of the bow tie shape. Everybody do this. We're going to talk about like left side, right side kind of stuff. Everybody do this at me. Because we're being the triangles. Do you see what I'm doing? Like, you're matching up, that's the tips of our fingers are like that vertex point in the middle, that V. Everybody raise your right hand. Do you see how it's opposite? You're raising, like looking at me, it's the mirror image. Does everybody see that? Raise your left hand. Okay? So what sides correspond in this? Yeah, I mean, we could say it as opposites. So if I write 3, what does it correspond to? 5. That's like right arm to right arm. Does everybody see that? And then, obviously, after that, what would go on the other side? Okay, so just think of it as that, like looking at somebody raise your right arm, it's the opposite side on them. So we get 3x plus 9 equals 10x minus 40. And then that's 7x equals 49. So x is 7. And we just plug stuff in. So BC is 6. And AB is 10. So I wanted to take time to talk through those since we hadn't really shown examples yesterday. How'd they go? Yeah, give me a rating. Let's do just thumbs this time. And not how much you did, but how did it go? Okay. All right, well, one other thing. Actually, I might do 2 of these. Let's see. But these kind, number 20, if we all look there, those kind can be kind of tricky. Why do you suppose? And there's different varieties of how these are presented to you, but what do you notice about them? How many triangles do you see? 2. Okay. What students will often do is start looking at this trapezoid. And you have to be careful. Is a trapezoid similar to a triangle? No. Now, you notice that those two, EB and DC, are marked as parallel, which gives us some different relationships that we can use. We'll learn that at the end of the unit. But for now, I want you comparing triangles to triangles. So on your paper, make that note. Do you guys want to put this one in your notes so that it's all together? Yeah? Okay. The concept isn't really different. It's just being careful with how you set it up. You have it in front of you. If you want to just take a second to draw it into your notes, it's up to you. All right. First step I recommend on these is to draw the two triangles separately. So draw and label. The two triangles separately. So when I look at this, I see a small one and I see a big one. Let's label the small one. What is the left side of it? When I say label, I mean with known information. What was it?
3.
It's 3. Okay, so 8 minus 5 is 3. And then the right side is x plus 2. And I'm going to scoot this one over. Okay, what's the left side of the big one? 8's right side? Yeah, x plus 2 plus 6. Or x plus 8. Okay. Set up your proportion based on the separate drawing. Okay, so it makes it a lot easier. And this is not a super hard one of these kind. So what is our proportion now? Or what's a version of it? What was it? Lyra, how about you set it up for us this time? Yeah, good job. I would describe that as left to left equals right to right. Does that sound consistent? Yeah, that sounds good to me. All right, and if we even were more specific, left little to little left to big left, and then little right to big right. So everything is consistent there. Yep.
Can I go to the bathroom?
Yep. Okay, do your cross product, set them equals, use your parentheses. And we'll get 3x plus 24, 8x plus 16. And that becomes 5x equals 8. So x equals 8/5. Huh? 1.6 if you want to make it a decimal. Okay, so again, the big idea of writing that note was this caution up here. Separate your triangles so that you're not mismatching parts. Students mess this up a lot, just so you know. And I don't know if it's like they're doing it hastily or just don't pay attention, but it's not that hard to separate your triangles and write the correct proportion. And then again, like I said, they come in various forms, meaning the information that's presented to you. And the fact that EB and DC are parallel will give us a shortcut, but I don't want us to learn it that way until we have this down. Any questions on that? Okay. So back to your sheet. I believe you're prepared now to do the rest of the problems from starting on number 21 through the end of the packet. So let's take some time to work on those. Any questions on that? We're all good? Okay, so finish up 21 through the end. And let's start with 20 minutes. I think I'll put a timer today. Of course, let's see. We'll have our break here in just a few minutes. So I'll include that in the timer. Just check answers. Any that were weird? Okay.
Now we got 4 guys.
So 21, again, fractions or decimals is fine. X was 14/5, and so FH is like 9.8-ish. So it's 21. Or 2.8, and then FH is 9.8. Number 22 is 14 for X, 8 for MN. Number 23 is 15 for X, 16 for AC. I can pause so you can check your proportions, make sure they're set up right. Can I go?
Yeah.
Great. 24, X is 6, Y is 4. 25, X is 9, Y is 12. 26. By the way, those two on 25 don't look similar to me. Do they look similar to you? So that's one reason that we rely on notation to tell us. And in this case, the two angles being congruent is the notation I'm talking about. Okay, 26. X is 4/3 or 1.333 and Y is 2. 27. X is 12.5 and Y is 3. 28. X is 5, Y is 4. And 29, X is 2, NM is 7, ML is 14. So, what was the hardest one on there, do you think? Like out of the ones you guys just did?
I'd say probably like 22, 23, 24, 25, 26, 27, 28.
Hardest. Okay. So 22 is weird. What else? Oh, Saphira's back there being like, this wasn't hard. Give me something that challenges me. That's what she's saying. 22. Okay. Any issues with 28? That one had the most going on in the proportion. It was okay? Okay. So in terms of, I would say this is setting up and solving proportions from similar triangles. Like specifically, that's what we just did. So let's kind of break it down because the next thing we do, you have to be solid in your setup. So fist to 5 in terms of setting up proportions from some kind of situation, like all these were triangles, but setting them up. Fist to 5, go ahead and rate yourself. Okay, so that's solid, good. And then this is more general. How about solving proportions? Any issues with that? So rate yourself fist to 5 on solving them. I feel like that seems to be going well. Okay, cool. All right, well. Just note, that's not it. All of those were triangles, but just before we did that, we did it with rectangles as well. As long as we know the figures are similar, we can set up relationships, right? The reason we do triangles so much is because they come up out in the real world a lot. Also, it's easier to prove that they're similar than other figures. So it's actually very easy in some cases to prove that they're similar. You'll do similarity proofs this unit, and they are the easiest proofs we do this whole year. Some of them are like 2 or 3 steps, and they're all almost always really easy. Let's just quickly review similarity. It says, explain why these two figures are not considered similar. They're not obviously triangles, but why aren't they similar? And don't say because they're not the same shape, which is true, but there's more to it than that. Okay, so the angles aren't congruent, right? Good job, Lyra. Okay, at least we have 2 of the same shape. What is the shape called? Okay, so why are these similar then? All right, so same angles. I'm going to be a little bit more specific while you think about the other part of the question. Corresponding angles are congruent. So corresponding angles are congruent, yep. And then what's the scale factor? What should you ask me? Yeah, which direction, right? So let's go little to big. Little to big. What's the scale factor? How about Mackenzie? Do you have to give me the decimal when I ask you that question? Hi. Or can you just write new over original? Right? That's okay, isn't it? It's not the best version. So Mackenzie, you can do that. Tell us what the scale factor is. Okay, so 4.5 over 3. That is technically a scale factor, or what we could call a scaling ratio. So if we multiplied all the lengths in the little figure by 4.5 over 3, it would give us all the lengths in the big figure, and we don't actually have to know the scaled down value. But when you do divide that, it gives you 1.5. Okay? Any questions on that? So this is okay as a scale factor. All right, this is kind of cool. You guys know what a truss is? It's like this is, by the way, a scale model of a shed. It's like the roof trusses in this one, although it's more complicated, the one in the figure. So it holds up the roof, right? Why is all this stuff in here? Yeah, lots of support. Okay. It's called a double Howe truss, and it's telling us that the width or the span of it is 42 feet, which is huge. Like that would go, this room is about 30 feet wide, so it would be another 12 feet past this. So this is a big truss. It would be heavy, probably have to lift it with the crane, I would guess. Also, it's 13 feet tall. This is called the king post. 13 feet there. So it says find the lengths of the missing supports. Now A and B are not labeled, but I will tell you it's these ones. Okay. And I'm going to give you a few minutes to try that. Please use what you've learned about triangle similarity and don't make this too complicated. Okay? In other words, I bet you can do it in 3 minutes, maybe less. You don't need to draw this. I will leave it up here, but you can if you want. But just please don't take the time to draw it and then not think through the work. So you're finding how long A and B are. Different than what you were doing, right? In fact, if we just zoom in like on this piece right here, doesn't that look like if you take out this piece, but it looks like the problems that we just got done doing, right? It's very similar. Okay. But our only givens are the 13 and the 42. So here's what I mean. You guys just got done doing a bunch of problems like this, where this whole thing is 21. Right? Okay. So maybe I try to solve for that one in this picture and try to solve for another one in the other picture. But I want to see how quickly you can come up with the pattern in this, because there's a pattern that will allow this to go much faster. Okay? Let's see how fast you can come up with it. So let's solve for A. Tell me what you know about other things I need to write in here for A. Like what else do we need in terms of information in the picture?
We need like the side, like the bottom, the base, and the bases.
Okay, like what?
I mean, it doesn't matter which one. You just need one of them, because then you could just subtract it from 21.
So this is 7, right? We already said that? Okay, so if we set up our proportion, what are we going to set up? You guys just rated yourselves out of 5, 4 or 5 on the sheet, right? This is easier than the sheet because there's really only numbers and one letter, one variable. Everybody agree? Okay. So 7 times, let's do 21A, and then 7 times 13 is 91. What's 91 divided by 21? What did you say? 4.3? And you said 13? Oh, well, that's the same. I thought you said 13 something 3. Okay, so that first support A is 4.3 feet or 4 1/3 feet. How many inches is 1/3 of a foot? 4 feet, 1 tick mark. How many inches is 1/3 of a foot? Okay, so it's 4 feet, 4 inches. Everybody good on that? We're in construction mindset right now. Nobody, if you walk to a job site and you said 4.33 feet, they'd probably laugh at you and call you a rookie, okay? So 4 feet, 4 inches. All right. I want you to think about the pattern that I'm talking about as I add B in here. What is going to change between this A value that we found and B? What changes in the ratio? Does this side change? No. What changes over here? The 7 becomes what? Okay, so what can you describe what happens from 7 to 14? What do we call that, just in casual language? It doubles. So what do we expect the b value to be? Okay, so that's, as long as these are evenly spaced. So how big is that? Let me write it first. 8 foot 8. Okay? As long as those are evenly spaced, we don't have to keep rewriting our picture and redoing our calculations. We can just double as we go. And think about if we had a truss, like a bigger truss, maybe it has supports all the way along here, right? And now you can double. So let me tell you this quick little story. You know, I used to teach GIC. And to do that, we had to go to a multi-day training with the people who wrote that program. And the oldest gentleman that was one of the writers, one of the creators of the whole GIC program, which stands for Geometry and Construction, by the way. He was probably in his 60s, had been teaching math for a long time. And he told us he went up to build his cabin, and he was building a truss like this with not just two, but repeated vertical supports. And he would go up and measure, come down and cut, and go up and measure and come down and cut, and just kept repeating that process. And he said he was so frustrated when it finally dawned on him that he could have just used proportionality and cut all of them at once and gone up there and plugged them in instead of doing all the measure, cut. And he was a math teacher, like he understood that, and it was like, oh, I didn't even think of it. So this kind of stuff is all around. Like building a shed is easy. I've told you that before. And you might need to do this for that, right? Instead of being the guy that measures, just cut, right? Like, meaning calculate and cut. So, interesting there. Hey, there's a proof. Should I send you home with that? All right, anyway, tomorrow's work is going to be probably the crux of the unit for most of you. Meaning means it's the hardest concept. Potentially, maybe not, but just study this tonight if you're a little shaky. It's not bad. I'm not saying it's hard. Just it's not proofs. We're not doing proofs. Oh, we're doing proofs next week.